today's lecture is called Total and Effective Stresses. Just very quickly, what is total and what is effective stress? Total is the total stress. If I have a building standing on the ground, then the total stress is the weight of the building divided by the area of the building. This is the total stress of the building. But this stress is going to the soil. The soil is not only soil, it includes soil and includes water. So maybe water is trapped below and it does not have the ability to move. In this case, it will carry some of the weight of the building. Some of the weight of the building will go to the water. The rest will go to the soil and will affect the soil. How can water carry load? Water or any fluid, water, gas, any fluid that is trapped in a container can carry load. If you have the tires of the car, what it is full of? Air. It's a fluid, but it is contained. It's under pressure. It cannot move, so it can carry a car. The football, the ball itself. You remember that one of the players standing on the ball, so it can carry a person. So any contained fluid can carry load. So we have just studied permeability of soil, and we said that some types of soil are very permeable and some types of soil are very less permeable. So like clay, if clay contains water and I stand on top of clay, water inside the clay won't leave it, but the permeability is very low. There is no gates for water to leave. Gates are very narrow, so they have to seep very, very slowly. So what will happen is that I will stand on the clay. Part of my load will go to the water and part of my load will go to the clay. So nothing will happen. The water will carry a considerable part. But as time passes, water starts to consolidate or to seep outside. So when water go outside, my load is going to be transferred to the clay, and the clay starts to be compressed more. So this is our introduction for this. Let's see what is written here. To design foundation and to ensure the safety of soil under the influence of structures located on it, the following steps are followed. Calculate the stress on the soil. Number 2, calculate the bearing capacity of the soil. Design foundation taking a proper factor of safety. So to design any building, then I calculate the stress, see the bearing capacity of the soil, and design the footing based on this bearing capacity. So I need to know the portion of the load that is carried by the soil. And then this is something about the factor of safety that we use in any building. If I know that the soil can carry 7 kilos, I'm not going to use the 7 kilos. Maybe I would take a factor of safety of 3 and tell you the bearing capacity is 2.5. Instead of 7.5, it is 2.5, and so on. So let's see what are the stresses on soil. Stresses due to own weight of the soil or stresses due to external loads. Let's see the stresses due to external loads. It's either a point load, a line load, or a uniform distributed load. This is general information. But what is important, the stresses inside the soil. The stresses inside the soil that is caused by own weight or by any other external load also, it will result in either a total stress and this total stress will be divided into pore water pressure and effective stress. So here it is not, they are not three equal things. The stress, it is the total stress, and this total stress is divided into pore water pressure and effective stress. Effective stress is the stress that the soil can take alone. Pore water pressure is the pressure of water. The pressure that they call it pore because water is inside the pores of the soil. So they call it pore water pressure. If I have, this is a building, so it adds a stress on top of the soil. This is the level of ground water. Then I have two things. I have, of course, vertical load due to the all the above loads, and I have a horizontal load of soil also. But there is a portion of this load that will be added due to the effect of the building, which is this portion. Stresses due to own weight of the soil. Here you were speaking about what is pore water pressure. There are many types of water inside the soil. Imagine that these four circles are the particles of the soil. These are soil particles. So what can water do in these four particles? It can either be a chemically combined water. It may be, the water may be included inside the particles. It may be chemically reacted with the particle itself, and it is included inside. So this is called chemically combined water. I don't see it because it is inside the particles, and I really don't care for it in my design for anything. I have something called hygroscopic water. Hygroscopic water is this thin film of water that is attached to the particle. By no means you can remove it unless you heat the sample. If I take the sample, heat it, maybe reach 100 degrees centigrade, so water will evaporate. This is the only way for it to go. But the chemically combined water, it cannot go because it is part of the, it is like my body, it includes water, it's inside. But if I put water on my skin, I can remove this water, I can flush it away. So this I cannot deal with. This I can deal with only if I'm subjecting the sample to very high temperature, so water will evaporate. I have capillary water. You heard about capillary water. Capillary water is the water that can rise inside the voids of the soil till it reaches a certain level, and it do not go beyond it because of surface tension, because of the suction forces that is developed inside the particles itself. The tension between the soil, the water, and the soil particles. You remember the capillary tubes? When you bring a very thin tube and you put it in a basin of water, what will happen? Water will rise in this tube, and it rises according to the thickness of this capillary tube. If you have thin tube, you may find water rising to maybe 5 centimeters. If you have wider tubes, it may be 2 centimeters. Wider, it may be no centimeters at all. So the voids of the soil resembles a capillary tube. So water can rise. It is a capillary tube, but it is not vertically up. It is it's swaying all around the particles. So as if in the soil you have millions of capillary tubes inside the soil. So water will rise in these capillary tubes till a certain level. So it is an added water for the particles, because the particles include voids. But these voids, due to capillary, water came inside these voids till a certain level. Free gravitational water, any additional water you can add. If you add water to the soil, if you just bring water, add it on the soil, the added water will go to the voids inside the soil. So this free gravitational, it's free and it is gravitational because it is affected by gravity, and it can move from one place to the other. If you put water here in one place, you will find that because the ground is sloping, it is seeping in another direction. So it can move according to pressure, according to anything can move. So this is free water. So these are the types of water we can find. Free water, capillary water, both I can get rid of easily, or at least they fluctuate easily. The capillary water, it changes from time to time. The gravitational water, it is all the time moving from one place to the other. The hygroscopic is very sticky to the sample or to the particles, so it does not leave it unless I force it to do this by heating 100 degrees centigrade. And this chemically bonded I cannot deal with. Types of water, it's either free held water, capillary water. This is what we just said. Let's discuss the free water. What is written here? It is the water which is located below the groundwater table. I have a level for in any place. If you go to the seashore and you dig a hole, you will find after a while that you have water reaching a certain level. This is the groundwater level at this place. In another place, you may find the groundwater level at 10 meters below the ground, or maybe hundreds of meters below the ground. So any water below this ground level is called the free water, because it moves from one place to the other. Its presence does not depend on the presence of the soil. It is if the soil is excavated below the groundwater table, this type of water remains. If I excavate a piece of land and there is water, I will end up having the water. Though when you remove the soil, you remove water with it, but once you finish drilling, you find that water came back again, because there is a certain level that water should reach. Whether ground particles are there or not, it's not their problem. It moves between soil voids under the influence of its own weight. That's why we said it is gravitational. It is not bound with the soil particles by any force. It does not require any energy to separate from the soil. It can move freely. That's why we call it also free water. It affects the soil under the groundwater with an upward force equal to the volume of the fluid displaced. It means that this water causes the upthrust force. This is the water that causes the uplift of any structure. Because it is free water, it is like water in a swimming pool. If you go in a swimming pool, you can swim. Why you can swim? Why you do not drown? Because there is uplift that carries you up. So this type of water can have this property, and it can carry anything above it. The other type is called held water. Held water is tightly bound by the soil by adhesion properties and is divided into structural water, hygroscopic water. So this is a little bit, we are adding categories. Structural water, it is the water that enters the chemical composition of the soil. So this is the first type that we have seen here. This one, and this one. These are bound water, they cannot move. So it is the structural water, it means it goes inside the structure of the particles and it cannot be removed. Hygroscopic water, it is part of the water is just covering the surface. But it is bound to this surface. It cannot leave it. If you want to take it away, you cannot take it away easily. So these are the held water, which are the hygroscopic and the structural water, or the water inside the chemically bound to the material. The third type is called capillary water. So now we have water below water table. This is free water. Water that is bound to any particle, whether above or below groundwater, it cannot move. So this is another type. The third type is called capillary water. Capillary water, as we said, capillarity is a phenomenon that we know in physics. When we take a small, very thin tube, put it in water, by surface tension and by capillarity, the water sticks to the sides of the tubes, and as if it is climbing the sides of the tube and goes above the level of the normal water at this location. Because that's why when you have wider tubes, it cannot take the whole water, because only the water at the edges will climb. But what about the water inside? It cannot climb, so the water is still in place. But if I have very thin tube, a thin tube means that all around I don't have anything inside. It is all a perimeter. It is just a very thin tube that the water, by surface adhesion and surface tension, they carry each other till they go up this tube. And we said that the soil includes thousands of these capillary tubes consisting of the voids of the soil. So these voids act as capillary tubes, so water can rise in this capillary fringe. Capillary fringe is the range above the groundwater table where water can climb by capillarity. So this is the level of water table, and this is the capillary fringe. If you are following me, you can answer my next question. If I excavate ground in a certain location and there is a groundwater level, and then water returns again, will it return to which level? To the capillary rise level or to the groundwater level? This is the groundwater table, and this above it there is still yellow fringe. This yellow fringe is called the capillary fringe, where water can climb through the voids and reach this. So it is above. If I now get workers and I dig here a big hole, water in this hole will be leveled. Of course, once I remove the soil will be removed, but water will still be there and will return to reach a certain level. Which level will it reach? Will it reach the level of water table or the level of the capillary fringe? Water table, this is correct. Why? You remove the soil. There is no capillary, there is no voids for the water to rise. It's just air. You now have only water. how water is going to rise beneath the level of water if there is air. So obviously it will return to the water table level. Yeah, this is just an example for how many centimeters or meter can water rise by capillarity. Sometimes by capillarity it may reach meters. Yani in clay it can reach meters. In soil and normal sand and just few centimeters. Now we reach calculation of the stresses. All of this I'm studying just to be able to calculate the stress at any point inside the soil. This is very important for me. If this is the ground surface, this is the groundwater table, it is a little bit below, and I take this column of water, a column of soil, and of course it includes water. There is here, this is the groundwater level, so this column is affected by water pushing up because it is like a swimming pool. This resembles me in the swimming pool, and this is the thrust or the uplift that is pushing me up to swim on top. So there is a force here, we call it U. This is water pressure pushing anything above it. Of course, water pushes not only above. What is important about water is that the stresses in water is in all directions. Water, if I am standing in a point inside the water, it means that water can push to the right, to the left, up, down, all with the same value. It is isotropic. In any direction, the stress can be applied. So one of the direction of application is up. So water can push now anything above it. What is above it? Above it is this column of soil, which has a weight of W1, and this column of soil, which has the weight of W2. You remember something about gamma bulk and gamma saturated? We studied this last year? No. So gamma bulk and gamma saturated, gamma bulk means the unit weight of soil in its normal shape. If I go to the site, bring a sample, measure the density or the unit weight of the soil, this value is called bulk because it is as it is in the soil. But because I have a sample below groundwater, then in this case, because of the effect of the uplift of the water, the load will be less. So what will happen is that the own weight here, W2, will be less than the own weight, W1. Imagine that they are both the same type of soil. This is sand and this is sand. This is clay or this is clay. It is the same type of soil. But if I measure the weight of the sample at this location, I will get a value. If I measure the weight here, I will get a less value. Why? Because it is submerged. It is below water and water is pushing. That's why we usually say something called submerged weight and bulk weight, or submerged unit weight and bulk unit weight. The difference between them is water, which is when we see a problem we can discuss it, but the difference between them is the effect of water on the sample. So the total stress at any location is equal to all of the layers above me. I multiply gamma, which is the unit weight, by h. If I am 5 meters below ground, what is the stress below ground 5 meters? It is gamma of the soil multiplied by the 5 meters. If I have many layers, then It's not just one layer, so it will be gamma of the first layer multiplied by the thickness of the first layer, plus gamma of the second layer multiplied by the thickness of the second layer, and so on till I reach the end. So it is the summation of gamma h, summation of all layers, gamma multiplied by its thickness. So this is h1 and this is gamma 1, this is h2 and this is gamma 2. Here gamma 1 is called gamma bulk, here gamma 2 is called gamma saturated or gamma submerged. That's okay, this we said. Pore water pressure. In case of water, the unit weight of water is 1, or it depends on the unit you are using, or 10 in case of using the different units. So gamma water multiplied by h. That's why you usually say that gamma water is 1, so that at any location the pressure of water is equal to the depth of water. If I'm at a depth of 3 meters, then 3 meters multiplied by a gamma of 1, it is also 3. So the stress or the allowable, the stress of the water is also 3. So this is the pore water pressure, or the stress of water, is gamma water multiplied by h of water. Effective stress. Effective stress, you can go to this equation. This equation say that effective stress is the gamma bulk minus gamma water, or the gamma effective is the gamma bulk minus gamma water. Anything we just said here, that the unit weight of the soil here is not the same as the unit weight of the soil here, though they are both the same material, because the difference is the unit weight of water. So here, if I say that this soil has a unit weight of 1.8, then this one will be 0.8 only. Why? Because I will subtract 1, which is the effect of water. Here, to understand, this is a very quick example. I have here, this is the ground surface, here is the ground level, and lots of layers. The difference is always in the gamma. Here, gamma saturated, gamma saturated, gamma saturated. Here, it is called gamma bulk because it is above the water table. If I tell you, calculate for me the stresses at these points, what will be the stress here at ground surface? If you have soil, layers, lots of layers, ground surface, what is the stress? Zero. You don't have anything above it, because the stress comes from above. Usually the stress comes from above. If nothing is above me, what is the stress on me? Nothing. I'm not carrying anything on my head. But if I can carry lots of layers, imagine that you are standing and nothing on top of your head. So what is the stress on you? Zero. If you take a book and put it above your head, so it will be the effect of one book. If you take 2 books, so it will be the effect of 2 books, and so on. So this is what we are doing. If you want to study here, then it is 0. If you want to study here at number 4, the stress will be equal to what? What you are saying is 50% correct. Why? Because you added the lengths. It is 12. This is h. You multiply h by gamma. Which gamma you are going to use? Here I have gamma 2. Here I have gamma 1.6. Here I have gamma 2. Here I have gamma 1.8. And I have water table. What? Summation. Yes, we are going to do summation. What we are going to do, if I want to calculate the stress here, the stress here is, this first layer is 4 meter. 4 meter multiplied by It's gamma. What is the gamma? 1.8. The next one, 4 meters multiplied by the gamma, it is 2, so it is 4 by 2, and so on. 4 by 1.6, 4 by 2. I add all of them together, I get the total stress at this point. It is the total stress. But if I tell you I need the effective, I don't need the total. I need what is the soil carrying without the effect of the water. So you have to exclude first the effect of water. Water starts from here. It does not start from here. It starts from here. So water the stress of water at this location is equal to how much? At this point? 0. Because this is, for water, this is the start of the water. For soil, the start of soil was here. But for water, the start of water was here. So at this location, it is 0. And the deeper I go, the stress increases according to the depth. The depth multiplied by gamma water, which is 1, as we said. So if I want to know what is the stress of water here, it will be 4 plus 4 plus 4, it is 12 by 1, so it is 12. So the stress here, it is 12 only because of water. This is what water can carry. But what is the total? We said that the total is 4 multiplied by 1.8, 4 multiplied by 2, and so on, the summation of all of these. Okay? Note? Here it is required that we draw the profile for the total stress, the pore water pressure, and the effective stress. So I need the total, what can water carry alone, and the remaining that is just carried by the soil. So I calculate at the ground surface, at the water table, at the start of the water table, and at the separation of each layer till I reach the end. This is our table. This is point 0, 1, 2, 3, 4. These are 0, 1, 2, 3, 4. And this is the total stress. As a start, the total stress for all the cases is 0. For this point, the total stress and the water table and the effective stress is 0. If I have a total stress is 0, then everything is 0. But if I go here, groundwater table is 0. So if you go here, you will find that there is an additional 0 here. Because for water, it starts from point number 1, not from point number 0. Let's calculate first at point 1, what is the total stress? 4 by 1.8. This is 4 by 1.8. Okay, this is okay. Point 2. It will be the 4 plus 1.8, which is the 7.2, it is here, plus additionally 4 by 2, 4 by 2, and so on. I go below. So I continue till I reach at the end, it is the total for the whole is 29.6. 29 is the summation of all of the layers, bulk as it is. The water, we said that the water will start from point 1, and as much as we go below, it will increase by 4 meters, because each layer is 4 meters. So 4, 4, and so on. So here it is 4, 8, 12. The effective stress, if I want to just to use my calculation, I will subtract. 0 minus 0, it is 0. 7.2 minus 0, it is 7.2. 15.2 minus 4, it is 11.2. It's just calculation, because this is what the soil can feel without the effect of water. So I take the total, subtract from it. Can I calculate this in one step instead of doing all of these tables? If I can tell you, can you calculate the effective stress at point 4 directly without doing all of these? You can do it. How? Like when you calculated the total stress, you multiply the distance by the bulk, and here the distance by the saturated. In this case, do not use the saturated, use the submerged, which is 2 minus 1, 1.6 minus 1, 2 minus 1. So in this case, you can calculate at 0.4 what is the effective stress without going into calculating the total and then the water and then subtracting for each layer. I don't need to do all of this. I will just stand at this point, start from above here. The first layer is 4 by 1.8. It has no water, so it will be 4 by. The second layer, it is 4 by, open brackets, 2 minus water, which is 2 minus 1. So it is 1, 2 minus 1. The third layer, 4 multiplied by 1.6 minus 1, and so on. So it is usually when you understand this, you don't have to do this table to reach this value. You can calculate it directly on the spot without. Even you can use sometimes without the calculator. You can calculate it with less number of layers. This is the drawing. This is the total stress taken from the table, and this is the water. The difference between the total stress and the water is that the zero starts from the first layer. It is because in this example, but if I bring you another example, water table at the top, then it will start from the top. No water table. Suppose I give you no water table, and I tell you get the effective. The effective will be the total, because you don't have water. It is easy. Then I just subtract both from each other to end up with the effective stress. Would you like to take a break now before going to the next part? Okay, we'll take a break. So this will be part 1 of our lecture. We'll stop here and continue the next part.